We are launching right away with things about the human foot by Shreyas Mandre.
Thank you, John-Luc. Thank you all for being here right after lunch, and I know many of you are jet lagged. I apologize to the few of you who may have seen this before, and if you're also jet lagged, then you can use that time. But I think many of you haven't seen this, so let me introduce you to the topic. It's about the structure of our foot. It's a collaborative work between myself, the group of Mahesh Bandi at Okinawa, and that of Madhu Venkatesan at Yale. These are all the students and postdocs who worked on it, and I'll be sure to show their pictures to highlight the work that they themselves did. There are multiple affiliations for each of them. So, without further ado, I would like to emphasize that it would be most beneficial and most entertaining if we incorporate the questions within the talk. If there's something that isn't clear, please shout or raise your hand, and I would like to resolve that question right there. I don't have too many slides, but I have dense slides, and so it's sort of enjoy the journey along with the destination. We will get to the destination, but the journey should, I hope, will also be pleasant. So the topic is our foot. Why do we have the foot the shape that we do have? And there are three components to it. There is obviously the structure-function relation of the foot, but there is also the evolution. We did not always, or our ancestors did not always have the same shape. So this journey begins about 8 million years ago, when our lineage, the human lineage, diverged from the chimpanzee lineage, and it's believed that the common ancestor had feet that resembled present-day chimpanzee feet or human hands. And the reason for that is the common ancestor was most likely arboreal, was arboreal, so had something to grab onto limbs. And about somewhere between 1.8 and 3.4 million years ago, and around the time when savannification of Africa happened, the structure of the structure of the human ancestral foot in the fossil record starts to show a deviation. So this is one from 4.4 million years ago, and it still resembles the present-day chimpanzee. But the next one, which I'm not showing in this picture, I'll show you later. The next one I'm showing is much later, 1.8 million years ago, and it pretty much shows all the structure that we have in our modern foot. So this is from Homo habilis, which literally means man with hands, who can work with hands. So why did the ancestral foot evolve from something that looks like a hand to something that looks like a modern foot, and why did it happen around the time that it did? So to sort of answer that question, we look at what do we use our foot for, and we use our foot to stand on it, distribute our weight on the body, but one of the primary functions that we use our foot for is to propel ourselves forward. So when we walk or run, I'm going to stand on the chair, and maybe you can see it, or some of you may not be able to see it. I apologize. So, yes, because this talk is about the foot, I'll stand on my feet. So when we propel ourselves forward, like in this picture, the instance then that we push off on the ground is with the ball of the foot when our heel is lifted. And during walking, especially during running, the largest amount of propulsive force is exerted at that point, and the foot is loaded under a bending load. It is as if it is clamped at one end and is supporting body weight or multiple body weights at the ball of the foot. And people who have flat feet, turns out, also have soft feet, and their feet bend severely even under just walking, regular walking. So it's even under walking, this posture for some is very painful. And one could see that the foot bends a lot by looking at this heat map of the maximum pressure during stance, during the phase that the foot is in contact with the ground. So this is one function. This is not the only function of the foot, but this is one function that I'm going to focus on. What makes the foot sufficiently stiff under bending to approximately body weight loads? So this is the central question. To answer this question, so just to highlight it a little more, because if it weren't stiff, if the foot were floppy like the flat foot, or imagine the extreme case with seal flippers, you try to push on the ground with a very flexible object, you most likely won't be able, you'll bend the object so much that it's as good as not having that object. So we consider what structural aspects attribute the foot its stiffness under bending. So we look at the structure. The structure of the foot is very peculiar. It has an arch structure. It has a doubly arched structure. There is an arch along the length of the skeleton, and there is an arch across the length, the transverse arch. And both these arches evolved in the fossil record after the split from the chimpanzee. Right? So I'm going to tell you my conclusion right away. Most of the clinical and evolutionary biology community focuses on the longitudinal arch of the foot. They think that is the structural feature that attributes the foot its stiffness. And there is some logic behind it. I'll explain it in a moment. But what I'm going to argue is that it's not the longitudinal, it's the transverse arch. Right? So let me first tell you the logic behind the conventional thinking. It is as follows. So if you look at the foot skeleton from the side, I have one right here. So you look at it sideways like this. This is the foot skeleton. We are looking at it that way. There is a soft elastic tissue near the bottom. It's called a plantar fascia. And some of you may have yourself or have had friends and colleagues have this thing called plantar fasciitis, which is an inflammation of this tissue. So when you bend the foot thusly, the plantar fascia gets extended and provides a restoring force, a restoring moment, and that's what provides the foot its stiffness under bending. That's the conventional picture. I'm going to invoke this again later. However, that picture does not quite withstand the scrutiny of quantitative analysis. There have been experiments measuring the stiffness of cadaveric feet with the interest of understanding during running, is it possible that the foot stores some elastic energy and then releases it to maximize the economy of running? That was the intention behind this study. So there were two groups who did it, and what both of them did was took a cadaveric foot, loaded it under a 3-point loading, so supported at two ends, and then loaded somewhere in the middle. But the point where it is loaded is so close to one of the supports that it can be considered clamped. It's a minor technical detail. I won't go too much into it. But the force displacement curves are plotted here. And this hypothesis that the plantar fascia, which is shown in this picture here, it's a white fibrous tissue, that's what is responsible for the stiffness of the foot, was tested by cutting the plantar fascia and doing the experiment again. So the bold curve here shows the load displacement curve for an intact cadaveric foot. Along with the plantar fascia, there are other soft tissue ligaments that connect bones that are not necessarily neighboring, and they also play a similar role in providing a cross-section moment to the foot. And they were also cut. So when this large ligament, which is right underneath the plantar fascia, when it was cut, the force displacement curve shifted from that one to that one. And there is another ligament that's right underneath, which is right there. When that was cut, the force displacement curve shifted from there to there. And finally, when the plantar fascia was cut, the force displacement shifted from there to there. So instead of having 2.5 millimeters of displacement for approximately body weight load, now we have 3.75 millimeters of displacement. So plantar fascia does contribute to the stiffness, but it's not even the dominant contributor to the stiffness of the foot. So where does the foot derive its integrity from? That's essentially the question I want to answer. And oh no, yes, sorry, I have to have a better arrangement. All right, so I'm going to give you my simple picture. If you have a thin elastic object, which is what I am going to assume the foot to be, and if you bend it in the longitudinal along its length, it remains floppy. But if you bend it in the transverse direction, now it becomes very stiff. That's basically the main message. And
That sounds great.
well, thank you for the interruption. I would expect more interruptions like this, not necessarily in the form of clapping, but so I'm going to try and argue this.
Oh, okay.
All right. So in order to describe or at least analyze this situation, I'm going to, for the moment, assume that the foot is analogous to a curved elastic shell, thin elastic shell. And that's so because the skeleton of the foot is indeed not very thick. It is about a centimeter and a half thick, whereas the length is maybe 20 centimeters, 30 centimeters, and 10 or 15 centimeters wide. And in addition, this is the more nuanced point, that what we want to investigate is the role of geometry. Clearly, the elasticity of the soft tissue and the constitutive law and the exact arrangement of the bones, all of those things matter. But if you want to abstract everything out and just focus on the role of geometry, then the curved elastic shell is a pretty good model, I think, because you assume the elastic properties to be linear and homogeneous. The number of degrees of freedom in the foot in the skeleton are high. There are, if you ignore the toes, there are 12 bones, 72 degrees of freedom. Pretty much every bone is connected to its neighbor by some elastic tissue. So if I were to make an approximation from the 72 degrees of freedom, instead of reducing all of that to a single spring, I would take the opposite limit and take the limit of infinite degrees of freedom to approximate 72. So postdoc with me, Marcelo, he developed solutions of shells loaded under conditions similar to the foot. And a postdoc with Mahesh in Okinawa, he actually built shells that are approximately the same size as the foot and with PDMS, and loaded them under the same conditions in an experiment, and measured the stiffness, which is for a given applied load on one edge, the other edge being clamped, applying a given displacement at one end, the integrated load, the force divided by the displacement in the small displacement regime is the stiffness, and that's what we'll monitor. So here is a little quantitative primer into thin shell theory. If you're familiar with thin shells, you probably don't need this, and the details are too many. But essentially, a shell stretches in plane, and that gives rise to an elastic energy proportional to the stretching squared. And also, locally, it could curve away from its undeformed curvature. So that's kappa. And it's also quadratic in that. There are different factors of thicknesses between these two terms. The first variation gives you force and moment balance, which is what we solve. We use a commercial finite element package COMSOL to solve these. And the boundary conditions that we apply on the loaded edge are that it's free to expand and contract in plane, no moments, no bending moments, and an applied displacement. Because of a detail in the shell theory, the force that is applied, it combines the shear stress and the applied twisting moment on the edge. This is a well-known mathematical feature of shell theory. So you integrate that force to get the density of that force to get the total force, and the limit of small displacements of the edge. The ratio of force to displacement is the stiffness. So now I'm going to plot this stiffness as a function of the two parameters, the curvatures of the shell. Actually, I'm not going to do that yet. I'm going to show you the sample solutions. So this is a shell clamped at one end, applied displacement. Sample solution is shown in this figure, also in this color map. The nature of the solution is such that for part of the shell, it behaves like an Euler beam, and that is indicated here by the green line being the neutral plane. So if this is the shape of the shell, that's where the neutral plane would be if you just assumed it were an Euler beam. And the black line is the zero stress contour from the computed solution. Because they agree in most of the in a large portion of the shell, that indicates that just beam theory would be a good approximation in part of the shell. But then there are departures near the edge, and that's the boundary layer. It so happens that the foot is in that parameter regime where this part of the shell dominates the displacement. It is as if having two springs in series, and the softer of the two springs determine the stiffness, and the boundary layer is the softer of the two springs. So in order to figure out the stiffness, you have to characterize this boundary layer, and this characterization is also not new. It's basically a competition between the stretching energy and the bending energy. That matching gives you a length scale for the boundary layer, and then scales for every other quantity emerge from that. Especially, this is the non-dimensionalization I would adopt. So you take the stiffness of the shell that we computed and compare it with the stiffness of an flat plate of the same dimensions, so just zero curvatures. Obviously, in the low curvature limit, we would get this ratio to be 1. But in the high curvature limit, there is using this length scale, the ratio of these stiffnesses approaches a particular asymptote, which involves the curvature. And in the general case, then one would argue that this ratio is only a function of that parameter, which non-dimensionalizes the curvature. So when this normalized stiffness is plotted against this normalized curvature parameter, variety of stiffness values collapse onto a universal curve. This is the zero curvature or small curvature limit, which asymptotes somewhere close to 1. There is a minor detail which I will explain if needed later. And this is the high curvature regime, in which asymptotes curvature to the power 3/2. And the crossover happens approximately around a non-dimensional value of curvature of about 10. So if I were to trust the shell model for a foot, I would say that the foot needs to be curved beyond this transition point for the curvature to affect the stiffness. So one would now examine the curvature of the human foot, especially the transverse arch. Oh, one more detail. These stars are all the points which only had a longitudinal arch. All the shells that had a longitudinal arch, they show no increase in stiffness. The ones that had a transverse arch, when the transverse arch is normalized this way and plotted on this graph, that's when you get this collapse. So measure the statistics. There are statistics available for the human foot, And the x-axis is purely geometrical. You know the curvature, the transverse curvature, you know the length and the thickness of the foot. You substitute, you get a value, and you get a number approximately there, which is not in the asymptote, but it is beyond the transition point. In addition, from those two experiments with the cadaveric feet that I mentioned, you can also get values for the stiffness of the foot. And if you pretend that a chimpanzee foot in all other respects is like a human foot except it is flat, so that gives me a way to normalize the dimensional value of the stiffness. Then k hat human, that horizontal bar, is from those cadaveric experiments. So this lies fairly close to the shell curve, which means at least the shell theory is not refuted by this comparison. Question?
Are you modeling it as a square?
Yes.
Okay.
I think there is already enough complexity.
Yeah, sure.
So to test whether this parameter is any good and is any useful, this is the extent to which data is available. And unless we do more experiments with cadaveric feet, it's very difficult to extend beyond this. So at this point, we just accept this as a tentative theory and move on. And now on the next slide, I'm going to actually Madhu from Yale. He applied this to human evolutionary biology, and he did it in the following way. So this is really exciting because evolutionary biologists, not Madhu, who is really a biomechanician, but already in the published literature, there is a way of estimating the transverse curvature of fossilized feet, even if only one bone is available, if it's the right bone. Right? And the way it is done is you look at the foot head on like this. Various cartoons are shown in this panel. So you look at the foot head on. The front of the foot lies flat on a flat surface, but the middle of the foot makes an arch. So if you look at the fourth of these metatarsals, which are these bones, the fourth metatarsal, therefore, must have a twist along its axis. Right? And for example, for the fossil Lucy, it's only the fourth metatarsal that was found, which was quite fortunate, because now from that angle, if you know that angle and you know the width, you can calculate the width divided by angle divided by the width would be the transverse curvature, and then you just normalize it with the other lengths that you have in the problem, and you construct the non-dimensional curvature. So Madhu did all. Sorry about that again. I hope it reappears. So Madhu did all of that, and in this plot, he plotted fossils versus this parameter, this curvature parameter. Remember, the transition for a shell happens around a value of 10 of non-dimensional curvature, which is this dashed line. So all the points except for this one, which was Lucy, fell to the right of that asymptote, which means that if the foot were a shell, then it would be stiffened because of the transverse arch, and it would be stiffened by a factor of 2, approximately 1.5 to 2, depending on the details. But for gorilla, chimpanzee, this is a macaque, and that's a vervet. None of those species have a noticeable curvature. So this is the first time, for example, I think we think this is a way of arguing that this organism, which left a fossil foot in Bertili, there is only a foot available, we don't know what organism it is, but purely from the structure of the foot, we could say that because of the arch, the foot had sufficient stiffness that it can propel itself on ground for walking, or most likely for walking, not for running. It's a little detailed question.
Could you compare the human hand and in gymnastics maneuvers or downward dog, you've got the weight on the hand, and in high performance gymnastics maneuvers, there's quite a lot of energy storage. Is that in the arch of the hand? Is there a known athletic technique for storing energy in the arch of the hand?
So I don't know the answer to that, but what I would say is that you're comparing millions of years of evolution with a sport that I don't know the history of, quite frankly. Therefore, I can't. For that reason, I can't compare. Yeah. But what is known about our hand is that it does not have. I'm going to describe the mechanism. The shell is too abstract a model. So I'm going to describe a mechanism. That mechanism is also absent in the human hand. So I'll come to that in a minute. So basically, I want to conclude here is that this foot of an unknown species, which existed, which is dated to 3.4 million years ago, the organism that left that foot probably walked on land as in a manner very similar to we do. And any other method of analysis, what evolutionary biologists basically do is they look at the bones. This is that fossil. This is from Bertilli. They measure different lengths and project those lengths on principal component analysis between gorilla, chimpanzee, and humans, and try to figure out which template best describes. And that process completely misses this feature. So by that process, this foot belonged to an animal much closer to the gorilla than to the human. But it's only when you interpret the transverse arch mechanically that you could conclude that it could support body weight for propulsion. So all of this is, I think to the extent that human evolutionary biologists integrate information, this is a useful piece of information, I would say. But as students of mechanics, can we say something more about why is it that the transverse arch matters? And I'm going to describe a simple model for just a 4 foot, right, from the midfoot onwards. So these bones that you see here, I told you these are called metatarsals, and their bases are attached to this transverse arch. Now observe what happens when I load each one of them. So I push on the first one, and it bends in a plane approximately that plane. If I push on the last one, you see it bends in a plane approximately in that direction. So I'm going to do it again facing this way so that everyone gets to see. If I push on the first metatarsal, it bends in approximately a plane that way. If I push on the last metatarsal, it clearly bends in a plane that way. So when I push on the 4 foot and load it under bending, you'll see that the metatarsals play a part. And that splay can be related to the arch because the arch determines the attachment and the local degrees of freedom of the joint, and that determines the predominant direction in which each of the metatarsal bends. Now it so happens that there is a reasonably stiff ligament connecting the distal ends, the far ends of these metatarsals, which means every time you have to bend the foot, that ligament also has to stretch, and there is additional elastic energy that's needed, which contributes to an additional stiffness. So that's the detailed mechanical model for why the transverse arch stiffens the foot under bending. And that's the mechanical reason why the twist in the 4th metatarsal really matters for the mechanics, which was heretofore not explained in this manner. So this is a good theory. We wanted to test it, and we wanted to test it in live humans because the ideal place to test such a thing would be in a cadaveric foot. We don't have access to those things. We have physicists and mechanical engineers and applied mathematicians. We don't know where to get a cadaveric foot. So Madhu and his group, Fernanda came up with this theory with me, and Madhu and his group, they developed a clever intervention in live humans. And So I have to do another demo because this is the movie that's not working. Okay. Remember, I told you about the plantar fascia, which is the tissue near the bottom of the foot. I'm going to stand on this chair. I don't know if you can see my foot, but those of you who can, what I'm going to do is, no, you can't see this way. Can I stand here? Oh, all right. All right. So this is the arch. Right? Now I'm going to twist my toe, and the arch height increases. It's very prominent. If you have a healthy foot, you can do this experiment at home. What you do is twist the toe and look at the arch height, which is the top marker on the top of the foot. Right? So that rises. So it is shown in those pictures there. With the live demo, if you can do it yourself, it's far more engaging. So why does that happen? This is a simple model for why it happens. So this is all the midfoot and the stiffness of the midfoot modeled as a single spring. This is the plantar fascia, and this is the toe. The plantar fascia attaches to the bottom of the toe. So when you flex this toe, it pulls on the plantar fascia. If this spring is really soft, then stretching the plantar fascia causes this triangle to increase in height. But if the spring is really stiff, then that joint cannot bend too much, so the plantar fascia stretches. So the amount of rise in the arch as a function of toe flexion is an indication of how stiff the midfoot is. All right. So what two of Madhu's students, Ali and Lucia, they built a little rig to do this a little more systematically. They have a rig, subjects stand on it and they flex their toe. There is a little more control that they describe it better than me why they do the experiment in a particular way, but they do. And they monitor the rise of this marker as a function. Now, remember what I told you, there is a ligament here that contributes to the stiffness. The ideal way to test this would be to cut that ligament and do the experiment again. But we can't do that. So instead, what they did was to tie an elastic tape around that ligament to reinforce it, to see if that increases the stiffness. And that's the, it's still slightly indirect, but it still captures the kinematics that I described. So there are two conditions. There is an untaped condition and there is a taped condition. In fact, there is a third condition called the control, in which they just wrapped the tape but did not tighten it, just to see if there was any difference from the presence of the tape. If you have no tape, as a function of the toe flexion angle, the arch rises a certain amount. If you put the tape lightly, the control, it roughly rises the same amount. But if you wrap it tightly, then that stiffens the midfoot, according to this logic, and the arch rises less, as expected. So this is a smoking gun. You don't quite have the body and the bullet. This is a smoking gun that this mechanism has some merit. This is my last but one slide. So what is interesting is that I demonstrated this with a 20-pound bill, right? And it works with a 20-pound bill. There are various pictures I showed with different structures. They all stiffen with transverse arch. The human foot, I hope I can at least argued that you will think about it as a candidate for the stiffness of the human foot. What's interesting is that this is a very general phenomena. We think it also acts in the fin of a fish. It's a little involved, and because I have a minute, I'll go into the detail. It's obvious that if I can take a flat elastic sheet and curve it and increase its stiffness. But is it possible to keep it flat but increase its stiffness by the same mechanism? Now remember, the mechanism was that when I push out of plane, it must bend in different directions. Neighboring rays must if they bend in different directions, that will stretch the elastic tissue in between. We think that's what happens. That is also possible that in a fish fin. If you look at, so this is a CT scan of the skeleton of a fin. These are rays, and the dark area in between the rays is the elastic membrane. If you look at a section like this, the rays appear like so, and the principal directions of bendings at that cross section are indicated with these crosshairs. And the numbers indicate their inclination to the horizontal. They are not all aligned. The principal directions are not all aligned. They're slightly misaligned, which means if I pushed on this ray, it will want to predominantly bend in one direction, and the neighboring ray would want to bend in a slightly different direction, and that will engage the membrane in between. So the same mechanism we think also present in the fish fin, even in a flat fish fin, which is the more interesting. So that's I hope that's everything I have to tell you. The interesting results are, we think the Bertillon foot, which was 1.6 million years older than what people today consider to be the modern foot, shows evidence of a transverse arch and therefore a human-like walking gait. And this is a very general phenomena that we think also exists in other animals. So it might be interesting to compare not just humans, but other load-bearing terrestrial species and their feet. Elephants. Actually, if you go to a museum, for example, the one in New York, look at an elephant foot skeleton, you'll see that it has a transverse arch. Once you start looking for it, you'll see it everywhere. So let me end with that note. Go look for transverse arches. Thank you.
Quick couple of questions for Shreyas. Back.
If I compare the stiffness of a flat plate with a cylindrical shell, the cylindrical shell definitely has high stiffness to bending, right? But if you compare a cylindrical shell with a doubly curved, say, part of a sphere shell, then the spherical shell has even more stiffness than the cylindrical shell, right? So then my question is, why the transverse curvature, or the one of the two principal curvatures matter? It should be the Gauss curvature or something.
So there are data points in here. So the diamonds are results from experiments, and some of those shells, experimental shells, are doubly curved. When we plot the transverse arch on the x-axis, only then do we get this collapse. All right.
Ask a quick one. When you run, your feet roll inwards. Is that at all related to the shape of the transverse arch?
Yes. So give me a minute to answer that. What I described to you was just one aspect of the structure-function relation of the foot, which is what is the transverse arch potentially doing. But we use our feet in many different ways, and especially when running. If you run, I don't know what your experience is, but I think it is possible to run on fairly uneven terrain without necessarily looking at the ground, or at least we don't have that type of laser sensors to know exactly to millimeter precision where the next landing is going to happen. So I think what running appendages, the way they are used is, on landing, you make a very soft contact. A soft part of the foot makes contact, and in addition, the foot is softened by the action of other muscles that we think relaxes the transverse arch to an extent. And that's why the arch is slightly weaker on the outside. That's why most humans, I think, land on the outside of the foot. And then you roll in. The toes are the stiffest to push on. That's where the transverse arch is the strongest, and this bending, stretching coupling is the strongest. So you push on the ball of the foot. And also at that time, you engage the muscles that reinforce the transverse arch to make it stiffer.
Thank you.